stopped our last class with the drawbacks of Bohr atom model, isn't it? Okay, the drawbacks we discussed, Bohr atom model. Okay, after that model came the quantum mechanical model of atom. Okay, quantum mechanical model, and there is a branch called quantum mechanics for that. Today we are going to discuss mainly two developments that led to quantum mechanical model. Main two developments that enhance the development of quantum mechanical model. Okay, that two important things or important points are the dual nature of matter and also Heisenbergs Uncertainty principle. Okay, both these developments came and that led to the quantum mechanical model. That led to quantum mechanical model. That are the things that we are going to discuss today. We have already studied about photoelectric effect and also black body radiation in the previous classes. Okay, both these phenomena can be explained by the particle nature. Okay, the particle nature of EM waves. By the particle nature we can explain both these two phenomena. We already studied them. Okay, then the phenomena or the processes like reflection, refraction, dispersion, interference and diffraction. Okay, all these phenomena of the properties of electromagnetic radiation. These are the properties of the radiations. Okay, they can be explained by the wave nature of EM radiations or electromagnetic radiation process a wave nature, isn't it? It has a wavelength, it has wavelength, then it has frequency, etc. we studied. Okay, all these phenomena we explain using wave nature, and the phenomena like black body radiation, photoelectric effect we can explain using particle nature of electromagnetic radiation. So from this it's clear that electromagnetic radiations possess both particle nature and also a wave nature. It has both particle and wave nature. Consider when electromagnetic radiations are interacting with matter. Okay, radiations when it interact with matter, what happens is that it shows a particle nature also. While electromagnetic radiations are propagating, okay, while gamma rays or while UV rays are propagating, it will show a wave property, isn't it? But when electromagnetic radiations interact with matter, it will also show a particle nature. So, this is the dual nature of electromagnetic radiation. That means an electron can also behave as a wave and also as a particle. Electron or electromagnetic radiations, okay, electron or electromagnetic radiations can both behave as particle and also as wave. Shows both wave nature and particle nature. So next, okay, we already know the equation. Energy of a photon is E is equal to h nu, isn't it? And we know the famous Einstein's equation. What is that? E is equal to mc square. E is equal to mc square. So you can equate both. mc square is equal to h nu. This is frequency h nu. Okay, where we can write m is equal to, or mass of the electron is equal to h nu by c square. Clear? Next, what is nu? It is c by lambda, isn't it? Nu is equal to c by lambda. So substitute that, c h by c square into c by lambda, where lambda is the wavelength. You can cancel one c. Then you will get m is equal to h by c lambda. Okay, this is an equation that is connecting both the particle and the wave nature of an electron. Okay, electron possesses a mass, that is the particle nature, isn't it? Possessing a mass is the particle behavior of a particular electron. It can also possess lambda or the wavelength. What is wavelength? It is the characteristics of a wave, isn't it? So m is equal to h by c lambda is an equation from we can understand electron or electromagnetic radiation can both behave as a particle and also as a wave. It was scientist de Broglie who found a relation between what the particle nature, or to show the particle nature, de Broglie correlated an equation connecting what wavelength and momentum. Connecting wavelength and momentum. De Broglie is a scientist who found a relation between what wavelength and momentum of particle. Between wavelength and momentum of a particle. Okay, the equation is lambda or wavelength is equal to h by mv. Okay, it is h by mv. H is the Planck's constant, m is the mass and v is the velocity. H by mv, which is equal to what? H by p. Okay, lambda is equal to h by p is an equation or the de Broglie relation. De Broglie relation of dual nature of matter is what? Lambda is equal to h by p, or lambda is equal to h by mv. Okay, wavelength is equal to what? Planck's constant 6.626 into 10 raised to minus 34 divided by p, which is the momentum of the particle, which is equal to mass into velocity of the particle. Next point is Heisenbergs Uncertainty principle. Okay, this principle is developed by scientist Heisenberg. It's a German scientist Heisenberg, and as the name says, it's uncertainty principle. Okay. It states that it is impossible to determine simultaneously both the position and exact momentum of an electron. Okay, it is impossible to simultaneously determine the exact position and the exact momentum of an electron. Mathematically, or this means what? It is impossible. Okay, we can't determine at a time. Okay, at a time simultaneously what? Both the position and also the momentum of an electron. Okay, at a time we can't determine for an electron both the position and also its momentum. Okay, we studied the contrary in Bohr's atom model, isn't it? But here this Heisenberg's uncertainty principle states we can't find both the position and velocity of an or position and momentum of an electron simultaneously. Okay, mathematically Heisenberg gave an expression for this principle, that is delta x. Okay, this is the simple delta x into delta p. Okay, this is into a dot is given. Delta x into delta p is greater than or equal to h by 4 pi. This is the expression given, where delta x is what? The uncertainty in position. Note down, delta x is the uncertainty in position and delta p is the uncertainty in momentum. Delta x into delta p is greater than or equal to h by 4 pi. Here h is the Planck's constant itself. Okay, in the previous or just now we have studied what? Momentum p is equal to mv, isn't it? Mass into velocity. So we can substitute what? M into v for momentum. So delta x into delta mv is greater than or equal to h by 4 pi. Okay, here mass is a constant, isn't it? So only delta comes for velocity. Since mass is a constant, we can take mass outside and mass goes down. If it goes down, what happens? Delta x into delta v. Okay, mv delta v is greater than or equal to h by 4 pi m. Okay, here this m went down. That is delta x into delta v. What is delta v? It is uncertainty in velocity of the electron. So we can say what? It is impossible to determine simultaneously the exact position and velocity of an electron. Or this Heisenberg's uncertainty principle states that it is impossible to determine simultaneously both the position and exact momentum of an electron. Mathematically, we can show it as delta x into delta p is greater than or equal to h by 4 pi, or delta x into delta v is greater than or equal to h by 4 pi m. Delta x is uncertainty in position, delta v is uncertainty in velocity, and m is the mass. Moving on to the principle of uncertainty, that is Heisenbergs Uncertainty principle. What is the significance? Let's discuss that. We already studied in core atom model what? Electron move in fixed orbits, isn't it? Fixed orbits, and we'll have what a particular energy, like that we studied. But here with this uncertainty principle we understood what? We cannot find for an electron both the position and velocity simultaneously. That is, this principle rules out the existence of what? Definite paths or trajectories, or the motion. We studied what? Only the electron move in that particular orbits, isn't it? It will not move elsewhere is what we studied. Only in that particular orbits the electron will move is what we studied. But this principle ruled out what? The existence of definite paths or trajectories of electrons. So there is no like that paths or trajectories, or definite paths or orbits are not present in the case of an atom for the motion of electrons. Next important point is what? This Heisenberg's uncertainty principle is only applicable to microscopic particles. Okay, it is only applicable to microscopic particles. That means for macroscopic particles or for bigger particles, it is negligible. Okay, that uncertainty is negligible. What is uncertainty principle? That means if you are finding what? Accurately the position of an electron, then when we find at the same time momentum, then that will be what? Uncertain. Okay, at a time, if we got both the position if we got accurately, then the value of momentum will be uncertain. Or if you find what? The momentum correctly or accurately, then the position will be uncertain. So this principle is applicable only to microscopic particles. To show that, I will give you an example. Look here. Milligram, isn't it? Milligram is a macroscopic substance, okay, compared to nanometer size, isn't it? 1 milligram is what? 10 raised to minus 6 kilogram, okay. For that substance, okay, for a milligram or a 10 raised to minus 6 kilogram substance, if we are finding what? The uncertainty in position or momentum by the equation, what? Delta V into delta X, okay, this is into sign is equal to, you put equality and find the value, h by 4 pi m, isn't it? This was the equation. That is equal to what? H value is 6.626 into 10 raised to minus 34 joule second by 4 into pi value is 3.14, and mass. Here we took what? 1 milligram, that is 10 raised to minus 6 kilogram. Okay, if you calculate this, you will obtain what? 10 raised to minus 28 meter square second inverse. 10 raised to minus 28. Is it a negligible value? Isn't it? It's a negligible value. 10 raised to minus 20. That much zeros ahead. So this is negligible. Okay, for a macroscopic particle. Now consider a microscopic particle or an electron. What is the mass of electron? We studied in the first class of this chapter. Mass of electron, proton and neutron. Okay, hope you remember. Mass of an electron is what? 9.11 into 10 raised to minus 31 kilogram. Okay, substitute the mass and find also delta V into delta X. Substitute H value. Okay, 4 into pi into mass of the electron. You will obtain what? 10 raised to minus 4 meter square second inverse is the value. But this value is not negligible, isn't it? This is a considerable value, 10 raised to minus 4 meter square second inverse. Okay. This example I gave you to understand what? This uncertainty principle is negligible in the case of macroscopic particles, and this is only applicable to microscopic objects or microscopic particles. These are the main two significance of uncertainty principle. After the development of dual nature of matter and Heisenberg's uncertainty principle came the quantum mechanical model of atom. Let's just learn what the basics of quantum mechanical model of atom. Quantum mechanical model of atom. Quantum mechanics is a branch of science that takes into account what dual behavior of matter that we already studied, wave nature and also particle nature. Quantum mechanics branch of chemistry or branch of science, it takes into account both the particle nature and also wave nature of matter. It deals with the study of motions of what microscopic objects which have both observable wave-like and particle-like properties. Mainly take into account microscopic objects properties and that will have both wave-like and particle-like properties. Quantum mechanics branch was developed independently in 1926 by the scientists Werner Heisenberg and also Erwin Schrödinger. Erwin Schrödinger got Nobel Prize in Physics for his development of Schrödinger equation. Erwin Schrödinger told that for a system, what does a system means? System is such as an atom or a molecule whose energy does not change with time. That is, it is time independent. Okay, for a system. System means an atom or a molecule whose energy of an atom or a molecule will not change with time. For that system, Schrödinger equation was developed. And the equation is what? H cap, H cap, this is called H cap, psi is equal to E psi. H cap psi is equal to E psi is the Schrödinger equation. Where H cap is what? Is a mathematical operator. This is a mathematical operator. Like d by dx, differentiation, integration. Similarly, H cap is a mathematical operator. It is called as Hamiltonian. H cap is a mathematical operator called Hamiltonian. And psi, psi is wave function. Psi is what? Wave function. It is wave function. It is called wave function. And also E is the energy of the particle. Total energy of the particle. What is Schrödinger equation? H cap psi is equal to E psi. H cap. This represents a cap-like structure. So it is H cap psi is equal to E psi. H cap is a mathematical operator and is called as Hamiltonian operator. This much only you need to study about Schrödinger equation. More detail it is not required. H cap psi is equal to E psi Schrödinger equation. Next, the important features of quantum mechanical model of atom we are going to discuss. Some of the postulates, main postulates we will discuss. Firstly, it tells what? It tells that the energy of the electrons in atom is quantized. Energy of the electrons are quantized. What is the meaning of quantized? Energy levels means each energy level can have what? Certain specific values. Energy of the electrons in atom is quantized. That is, it can only have certain specific values. Second point is the existence of quantized electronic energy level is a direct result of what? Wave-like properties of electrons and are allowed solutions of Schrödinger wave equation. Schrödinger wave equation we studied. H cap psi is equal to E psi, isn't it? Where psi is a wave function. This is Schrödinger wave equation, taking into account the wave characteristics. Different electronic energy are existing as a result of wave-like properties of electrons and are what? The solutions of this equation. In mathematics, we have already studied equations and their solutions. Similarly, the energy values are the solutions of this equation. Third point is what? The Heisenbergs Uncertainty principle itself. That is, both the exact position Position means delta x, isn't it? And also exact velocity delta v of an electron in an atom cannot be determined simultaneously. Heisenbergs Uncertainty principle, and the path of an electron in an atom therefore can never be determined or known accurately. We can't determine the path of an electron in an atom accurately. That is the third point. Fourth point, an atomic orbital is a wave function psi. Okay, psi is what? A wave function is what I told you. An atomic orbital. Okay, atomic orbital is a wave function psi for an electron in an atom. Whenever an electron is described by, when we are describing an electron by a wave function, what we say? We say that the electron occupies that orbital. That means an atomic orbital is what? A wave function psi. We can explain an atomic orbital by a wave function psi. An electron is described by a wave function. We say that the electron occupies that particular atomic orbital. Fifth and the last postulate or the last point we can say. This is an important point. Okay. The probability of finding an electron at a point within an atom is proportional to the square of the orbital wave function psi square at that point. Okay, we can't define accurately the position of an electron is what we told, but we can say the probability. Okay, what is the meaning of probability? You already know, isn't it? We can't say exactly, but we can give a probable idea of the presence of electron. Okay, probability of finding an electron inside an atom. This is the nucleus inside an atom. Okay, the probability of finding an electron at a point within an atom is proportional to what? The square of orbital wave function. If P we are representing as what? The probability of finding an electron at a particular point here. Okay, at a particular point here, if we are saying or if we are going to tell about the probability of finding an electron at this point, that probability is what? Directly proportional to square of wave function. That is given here. It is directly proportional to the square of orbital wave function or psi square at that point. Okay. Probability if there at a point. Okay. If at a point there is electron or not. Okay. The probability of seeing an electron at a point inside an atom is what? Proportional to square of the wave function. Okay, at that point, what is the square of the wave function? That will give you the probability whether an electron is present there or not. And the psi square value is called as probability density. Okay, the term is probability density and the probability density will be of always a positive value. Okay, from the value of this psi square at different points with an atom, it is possible to predict the region around the nucleus where the electron will be most probably found. Okay, that is inside an atom. This is the nucleus. Okay, we will find the probability psi square value. Square of wave function psi square value we will find at different points and their values of psi square will give you what? The region. An accurate region cannot be defined, but a probable or a possible region around the nucleus where you can see what? The electron. It is possible to predict the region around the nucleus where the electron will be most probably found. These are the main significance of quantum mechanical model. The next class we will explain about orbitals and also about quantum numbers. That's all dear students. I am going to conclude today's class. If you have any doubts you can comment down. Be prepared for the live class. Thank you and have a nice day.